Hello, everybody. Today we're going to be talking about communication receivers. This is chapter 9, and it's the last lecture of the class. So um, here we go. We start out with some key terms. First one is a mouthful, super heterodyne receiver. It's the most common form of modern receiver. It's a very clever system. We'll be talking about that today. Selectivity is another key term. Basically, we're using tuned circuits to isolate stations from one another. And then sensitivity is another key term, which basically comes down to gain versus noise. How much gain you have and how much versus how much noise you have. Signal to noise ratio is a big topic, which we'll be talking about towards the end of this lecture. Common term is MDS, minimum discernible signal. What's the smallest signal that can be received by a receiver? And that has to do with its sensitivity and, of course, noise. Sensitivity is expressed in microvolts or dBs above a microvolt or dBs above a milliwatt. There's a couple of examples here. Receiver, we have an antenna input impedance of 50 ohms. Sometimes it's 75 ohms, but we're using 50 ohms for this example. A 1 microvolt signal produces power across the 50 ohms of 2 times 10 to the minus 14 watts. So it's B squared over R. All right. Expressed in dB, it's going to be 10 log. Now this is reference to, reference to a milliwatt. So this is that power divided by a milliwatt times 10, and then to take the log of that times 10. So dBm is the expression for dBs above a milliwatt. So it's 2 times 10 to the minus 14 divided by a milliwatt. 10 log of that is minus 107 dBm. If a receiver has a sensitivity of 10 microvolts, expressing that in dBs is 20 log times 10, it's 20 dB. Sensitivity above a milliwatt, 20 dBm is 20, that 20 minus the 107 up here is minus 87 dBm. So that's the sensitivity above a milliwatt. If you're looking at a half a microvolts sensitivity, that translates to a sensitivity of 20 log 0.5. That's 0.5. It's above a microvolt. Ends up with minus 6 dB. Okay, and so your dBm number in that case is minus 6 minus 107 is minus 113 dBm. Okay, so there's some sensitivity examples and how we express sensitivity of a receiver. We talked about crystal radio before. This is the simplest set, simplest receiver. It's a crystal detector, diode detector. I think I brought it in when I made. Here's the tuning section here. This is the tank circuit, tunable tank circuit, your headphones. These are piezoelectric headphones. But modern receivers are super heterodyne, and basically what it means is it converts all incoming frequencies to a lower fixed frequency. And that is really nice because that means the rest of our receiver that handles that lower fixed frequency, one, it's lower, so it's easier to deal with, right? High frequencies are difficult to manage. Also, those high frequency means you have to have a lot wider bandwidth for the rest of the system. So it allows noise to come in. So the lower the bandwidth, the lower the noise. Okay. The lower fixed frequency is called the intermediate frequency. All right, it's IF, short for intermediate frequency. Super heterodyne receiver consists of a mixer, a local oscillator, the IF filter, okay, a demodulator, and automatic gain control circuit. We have a block diagram here, right here. Here's the antenna coming into the RF amplifier. We have a mixer. The mixer mixes these two frequencies. One comes from a local oscillator and the signal frequency. We'll talk about mixers in a moment. And we have intermediate, that creates this intermediate frequency, all right? We have these amplifiers here that amplify the intermediate frequency. A filter, which filters out just the everything except for the intermediate frequency. And then we have a demodulator, automatic gain control circuits here. Okay. Okay, a mixer works to take two frequencies, okay, and mix them together. What happens is you get four frequencies in the output. You get the local oscillator frequency, which is FO, plus FS, which is the signal frequency. You get the difference of the two, so you get the sum and difference, and then you get them individually. Sometimes that happens, sometimes it doesn't, but let's say for this example, you get all four of these frequencies. Then you filter out just one of them, just one of these. Usually it's the difference, F0 minus Fs, to create this intermediate frequency. You filter it using a tuned circuit, okay? Usually it's a low-pass filter or a band-pass filter. Now notice this local oscillator. I have this arrow going through here because it's adjustable. All right, so it selects the specific station where F0 minus Fs equals Fif, the intermediate frequency. So understand, this is a fixed frequency. This is like 10.7 megahertz on the output here. Always. Doesn't matter what station that's coming in here, the difference, the F0 minus Fs, always is going to produce 10.7 megahertz, let's say, for this example. And that's what this tuned circuit is designed to filter, only 10.7 megahertz. So if another station's coming in here at a frequency that doesn't result in F0 minus Fs, this local oscillator being tuned so that the resultant IF frequency is not 10.7 megahertz, it's not going to get through, okay? So this is how you tune the receiver, is tuning your local oscillator, changing its frequency so that this product or sum or difference, F0 minus Fs, equals 10.7 megahertz, okay? So here's an FM radio receiver, which has 107.1 megahertz. It's going to translate it to 10.7 megahertz. The reason I use that is because that is a common IF frequency for FM receivers. It's going to create that IF frequency, and it's going to amplify it and detect it, demodulate it. So the local oscillator frequency is 96.4 megahertz. So you tune the local oscillator to 96.4 megahertz so that when it mixes with this 107.1, it creates 10.7, okay? So Fs down here minus Fo is 10.7, you see? If you want to tune to a different station, okay, you tune your local oscillator so that the F0 minus Fs, all right, difference still equals 10.7, but your Fs is a different number here now, okay? So this has to be a different number, all right, your local oscillator. All of it has to create 10.7 megahertz. So that's how FM radios are tuned, and AM radios too, in a super heterodyne system. Now the problem there's only one problem with these IF receivers is that you can get image frequencies. An image frequency is a frequency that occurs at 2 times above and below the signal frequency, 2 times the intermediate frequency. Okay, so if you have 10.7 megahertz, for example, that'd be what, 21.4 megahertz above and below the signal frequency. The problem is that's kind of close to what you are trying to listen to, the signal frequency. So what you can do, okay, is, so here it is, another example of it. 2IF up here, 2IF down here, and here's your desired signal. This is pretty close to your desired signal, so you're going to need a pretty good filter, all right, to get that, to get rid of the image frequencies. And you can do that, but it might be expensive or lossy, all right? There's 2 other ways of fixing it. One is with a dual conversion receiver, and one is a direct conversion receiver. All right, the dual conversion receiver has two IFs, okay? It's an RF amplifier here. The first mixer is adjustable, or I mean the local oscillator is adjustable. It takes the input from an adjustable local oscillator to create, again, this 10.7 megahertz. And then the second local oscillator is fixed. It's a fixed frequency local oscillator going through a second mixer to create a second IF, which is 455 kilohertz. Again, very common. All right. Then these IF amplifiers come through and a demodulator. So this completely retranslates the frequency using the second mixer and removes the image frequency problem. So this is very common to be done. Okay, so here's an example. Okay, we want to tune from 220 to 224 megahertz. First IF is 10.7 again. Second IF is 1.5. So the local oscillator tuning range is going to be 220 plus 10.7, 224 plus 10.7. So these two local oscillator frequencies. All right. That's so that when you mix this, like the 230, with the incoming 220, you get 10.7, okay? And the same with the 234. So the local oscillator tuning range is 230 to 234, 230.7 to 234.7. So the second local oscillator frequency is 1.5 megahertz higher. So you're going to get 12.2 megahertz for the second local oscillator. And so here's your first IF tuning range is 241.4 and 254.4. So it's just simple arithmetic, really, to get through these. A direct conversion receiver, a little different. It converts everything right down to the baseband. Okay, so basically the local oscillator frequency is the signal frequency, and the sum and differences, you end up with 0 in one of them. And the sum, you end up with twice the signal frequency. If you use just a simple low-pass filter here, all right, you end up with a demodulated baseband output. Basically, the sum is 0, or the difference is 0, FLO minus FS. You get 0 frequency here. So you end up with the demodulated baseband output for a direct conversion receiver. The problem is you can't do FM or frequency shift keying or phase modulation or phase shift keying. You can put two mixers in, but it gets kind of expensive. But it can be used with continuous wave AM, SSB, or DSB, okay, dual sideband. So it's useful, pretty simple. There's also the software-defined radio, okay, where basically we take the intermediate frequency, we digitize it, okay, and then everything else goes to a DSP, digital signal processor. For those of you who are doing Arduino and Raspberry Pi projects, there's some projects that are available online where you can make a software-defined radio using your Arduino and Raspberry Pi boards. It's pretty cool stuff. We used to do projects with this, okay. Basically, it's all this up here up front, the low noise amplifier, the mixer, the local oscillator. This is all analog, okay? And then the mixer creates the intermediate frequency bundle, and that gets digitized, all right? And so the rest of it, this intermediate frequency, is all sent into the digital signal processor, and away you go. So it's very quiet. Let's talk about noise, my favorite subject. You all know the bigger the bandwidth, the bigger the noise, right? Wider bandwidth equals more noise. But it's also related to temperature. So noise is related to bandwidth and temperature. So the higher the temperature, generally the higher the noise. We measure noise in comparison to signal. That is referred to as a signal to noise ratio, and it's measured in decibels. Okay. Signal noise ratio, you can have voltage signal versus voltage noise, or noise signal voltage versus over signal over noise voltage, or you can get signal power over noise power. Either one, okay? Most of the time we use power, okay? But we also have signal voltage here too. For voltage, it's 20 log signal over noise. For power, it's 10 log signal over noise. For the voltage, obviously this is signal voltage over noise voltage. For power, it's signal power over noise power. Here's an example. We have 1.2 volts or microvolts over 0.3 microvolts is 4. All right, so signal over noise 20 log 4 is going to be 12 dB. That's for voltage. All right. Now, if you're doing power, let's say we have 5 microwatts. This is signal power. Noise power is 125 nanowatts. That's going to be 40. 5 times 10 to the minus 6 divided by 125 times 10 to the minus 9 is 40. So we have 10 log 40 for power, 10 log, which is 16 dB signal and noise power. Okay. If ever it's less than 1, it's going to be a negative value, right? That's always the way with logs. All right, where's noise come from? Industrial noise is one place. Automotive ignition systems, you know, noisy spark gaps, things like that, high voltage switching circuits. We have atmospheric noise, usually by lightning. Okay, it affects RF systems less than 30 megahertz usually. There's noise from outer space, solar flares or cosmic events. Affects RF systems in the 15 to 115 megahertz range. Internal noise is something we fight all the time when we're designing things. Adjacent circuit elements, inadequate shielding, or high frequency circuit isolation. Thermal noise, which we'll talk about. Thermal noise is random white noise caused by electronics traversing conductors and counting thermally agitated atoms. So any resistor has thermal noise in it. Anything that's running current through it or getting hot is going to create more noise. So you try to keep your circuits cool. That's why they have the cryogenic astronomical telescopes, right? Radio telescopes. They're cool to superconducting low temperatures. And we have semiconductor noise, which is called shot noise. Anytime there's a discontinuity in silicon junctions, the PN junctions, you get this noise current, which is a shot noise, okay? Semiconductor noise is what it is. We express noise levels in a couple different ways. One is with noise ratio, also called noise factor. Don't let that confuse you though, but noise ratio, which is the signal to noise of the input divided by the signal to noise of the output, right? And then there's noise figure, which is a noise ratio expressed in decibels. So it's noise figure equals 10 log noise ratio, and that's in dB. Here's a little example. I have a noise ratio of 8 divided by 6. All right, 8 is the input, 6 is the output. Noise ratio is 8 over 6, 1.3333. Noise figure is 10 log 1.3333, which is 1.25 dB. Noise temperature, if you have a device that's getting hot, all right, you take that noise ratio, -1 times 290, that is your noise temperature. Another way of expressing noise. And we have thermal noise voltage. Notice the T and the B and the R. Well, the T is the temperature in Kelvin, which is degrees C plus 273. B is the Boltzmann's constant. R is the resistance. B is the bandwidth. K is the Boltzmann's constant, I'm sorry. B is the bandwidth. But notice the positive correlation between bandwidth and temperature. It raises the noise voltage. So here's an equation which shows the relationship between bandwidth and temperature and noise. Higher the temperature, the higher the bandwidth, the higher the noise. Here's a little example, a little plug and chug, 100K resistor, 25 degrees C, 20 kilohertz. All these values in here, you get 5.74 microvolts. Not much, but it's something. You can actually take a 1 meg resistor, put it on a scope probe, and look at the thermal noise in that device. Shot noise is a current, actually, in a transistor. Transistors are normally current output devices, so that current fluctuates with the shot noise. But notice we have B here again, the bandwidth. All right, there's a positive correlation. It's in the numerator, in the top part. There's no denominator, but okay. And here's a little example, a little plug and chug, 0.1 milliamp, 12.5 kilohertz. Here's the noise current. Okay. Another way we look at noise, or to express it, is along with noise and distortion. Sometimes you want both of those things. So we have signal plus noise plus distortion of the composite signal divided by the noise and distortion of the receiver. So this is what's coming in, S plus N plus D, of the composite signal. It's not perfect. It's got some signal, it's got some noise, it's got some distortion. But then you put it through the receiver and you got noise and distortion of the receiver. So SINAD, we call it, signal plus noise and distortion, is 10 log signal plus noise and distortion, and then the numerator divided by noise plus distortion, and that results in dB. Okay. This is pretty common in audio. We use this. Okay, in cascaded systems, the first stage, if you have like many amplifiers with each one with their own noise noise ratio, okay, the first one contributes the most. It makes the biggest difference. So that noise ratio has to be the best performing amplifier. That amplifier has the best noise ratio of everything, because the other ones don't make as much difference. That's why you have the LNA, the low noise amplifier, right up the satellite dish. Very high performance amplifier right there, because if it isn't, the rest of it's the whole system's gonna be noisier. The other ones don't make as big of a difference. So the whole overall noise ratio is given by this freeze formula. NR overall is NR1 plus NR2 minus 1 divided by A1, amplifier, the amplification of the first one, plus NR, the noise ratio 3 minus 1 divided by A1 times A2. So every time you go down one level, all right, you're dividing by more and more because of these amplifier numbers down here. Get them multiplied together. Power gain of the first amplifier, power gain of the second amplifier, and so on. An example is if you have this noise ratios of 1.6 and then 4 and 8.5 of these cascaded amplifiers, and 7, 12, and 10 are the power numbers for the power amplification. Running it through this formula, you get 1.6, that's the first one, plus 4 minus 1 over 7. Okay, 4 minus 1 is NR2 minus 1 divided by 7 of the first, and so on. You end up an overall of 2.12. Well, notice the first one was 1.6. Well, that's a big percentage of that 2.12, showing that this first one here makes the biggest difference, right? That's the biggest difference, or the biggest contributor. The noise figure is 10 log of the noise ratio. It's 10 log of 2.12. You end up 3.26 dB. Okay, so that's that chapter on noise and receivers. So if you have any questions, post them please in the discussion section of our Canvas site. Okay, thanks.